I drew a
Good job, Mr.
diagram.
Gomez.
Thank you. Thank you very much. I drew a diagram. Here is the charge that's fixed. Okay, a fixed charge means it can't move. That's a target. And we shoot this positive Q at the charge, the velocity V. I labeled that Q, right? How am I looking? Okay.
Yeah,
I guess I should have wrote a little tiny M here, shouldn't I?
it's fine.
Now, you look at my math and tell me, are you doing the same sort of thing? Are you saying energy initial equals energy final? Are you writing kinetic energy initial plus potential energy initial equals potential energy final? This, a lot of people like to skip some of this stuff. I've been warning you. So what is the initial kinetic energy? 1/2 mv squared. Now, how did we know what the final potential energy is? K, that Q over R is the, over this R, is the initial voltage. And this voltage times that Q would be the energy, potential energy. So Q times voltage is potential energy. We didn't have to do any calculus because we already did that, so we're just using the formula. And then that's the potential energy final. Everybody got that?
Mm-hmm.
Is this what you got?
Yeah.
I just got to check something. Yeah. I got to make sure that I don't screw up and come up with a negative sign in here, right? Like,
That's fine.
the final distance is smaller than the initial distance. But because it's on the bottom, it works out to be positive, correct?
Mhm.
Okay. Now we're going to look at the infinite line. And Jordan Totten, I am sorry I didn't see your email earlier, but she did have a valid point, and I should really specify this. Where's my annotating tools? The question is, could it have been one of those problems where we had an infinite line and my charge is over here and it's coming this way? And this is along the x-axis and this is the origin. You follow me?
Yeah.
Did everybody assume it was like this? The charge is being shoved at the middle of the infinite line?
Mm-hmm.
All right. Well, that's the way we've done problems like this. And I don't know why I didn't even think of that, but that's the case. Okay, so this is what I did because that's what I had in my head. I'll change that if I ever use this handout again and be more specific. Again, you start off with the same thing: energy initial, energy final, kinetic energy initial, no big deal. But this is weird. How can I say the potential energy initial is 0? I am saying that I get to set the 0 level anywhere I want. And there's a reason why. And I'm going to draw a picture and give you a little background on this, and I hope you don't fall asleep on me. Mason is in the house. Hold it. Okay. Here's what I want to say. If I made a graph of force, here we go again with this stupid thing. Something's wrong because sometimes it does this to me. I can't type again.
It means there's something in front of your window that you're looking at.
Look, I've been doing Zooms now a lot, and I don't get it. I shoved that thing. Nope, it won't let me. Let me turn off this, and I'm going to come back on with this, and I'm going to go over here. Now it worked. Okay, I just turned off the bar and turned it back on again. Okay, so let's say this is the force, and down here is going to be the distance. For this infinitely long wire, the curve is going to look like this. Now, do you remember deriving the formula for this? Using Gauss's law? Here we go again.
Did we use a cylinder?
Yeah. You use the cylinder. I'm gonna have to turn that off again, turn it back on again. Weird. Force will be proportional to, do I have a proportional symbol? I guess that is proportional to 1 over x. Does anybody remember that?
Mm-hmm.
Thank you. That means that the area under this graph is going to be the work done for me to bring this charge inward. The potential energy, therefore, will increase. A 1 over x graph is not the same as a 1 over x squared graph. Now, I think you've probably talked about this in your math class. If I go from an infinite distance and I approach this wire, the area under this graph, 1 over x, will be infinite. The area under the 1 over x squared graph will be a finite value. Does anybody know what I'm talking about?
Yeah.
Okay. That is why they tell you that when you're doing a problem like this, it's the difference in potential energy from here to here. And I might as well call this 0, because if I call infinity 0, I'm going to have an infinite potential energy by the time I get to here. Does anybody know what I'm talking about?
Mm.
It's the same story as down here. I can't say the particle has 0 PE when x equals infinity, because as I come into this force, I'm going to have an infinite energy. So you set the potential energy to be 0 at some place. We don't do that here. We say the potential energy is 0 at infinity, and it works. Everybody has agreed to do that. As I come in, when I get to this point, I'll have a finite PE. So we can talk a little bit more about that, about the graphs, if you want to, a little later. Got a little story I could tell you about that. I think I already told you. So where did this formula come from that I'm using for the voltage?
Is that the integral of force?
Yes, it's actually the integral of the electric field. You could look this up in the book, but you probably could also take the integral, which is actually what I did do. You know what? I'm going to do, what am I doing? We talked about this just the other day. The electric field is going to be equal to lambda, right? Times L. That's the Q inside over what? Epsilon naught times the area of the Gaussian surface, 2 pi r times L. Tell me if that sounds familiar. Even if it doesn't sound familiar, I don't care. We did this in class. Actually, maybe I should write it like this. Lambda over epsilon naught, and then we got the 2 pi. Whoops, this is really horrible. 2 pi r. So it is 1 over r. If you take the integral of this, this is r to the minus 1, and that's where you get the natural log from. And then, of course, you got to plug in your limits. Does any of that sound familiar to people? The negative sign allows us to say that if I'm going against the field, my voltage will increase. Okay. Somebody's typing like crazy. What is that? All right. Well, anyway, all I wanted to do was take a look and see that similar problems may have a very different outcome because the field is dropping off here as 1 over x squared. Here, the field drops off as 1 over r, and you end up with two very different equations. And of course, this one, if you recall, you have to fight that field. So it's just the work that you're doing increases the PE. And this is going to be Q times E, which is a force, times a distance. And I'm setting my potential energy to be 0 right here, which makes sense. And sigma over 2 epsilon naught, that is the electric field. Does that sound reasonable?
Mm-hmm.
Yeah.
Okay. Look at the cool graphs, kids. Graph A. Look at graph A. What is that general relationship? F is proportional to?
One over x.
For A, F is proportional to 1 over, I couldn't hear you really.
1 over x.
1 over x squared, isn't it?
Oh, yeah.
That's the force. This is force, right? Is everybody with me?
Mm-hmm.
Adriel, all you got to do, I'm going to get
I'm here.
When you graduate, I want a button on my computer for next year's Zooms, and I'll press it, and it'll be your voice going, mm-hmm. I'll feel so much better.
I'll make a program. I got it.
That would be really cool. Every randomly now and then I get a, mm-hmm. All right, so this is 1 over x squared. What's B? Do I have to pay people money or what?
1 over x.
It is. It's 1 over x. Thank you, Malav. I appreciate that. Why are they intersecting? At x equals 1, what's going to happen, Dean? He's not going to talk to me. He's not even there. I think he went on a Boy Scout camping trip. That's what I heard.
After x equals 1, the denominator starts growing faster for 1 over x squared. So
Yeah.
it's smaller.
Yeah. So right here at the intersection, 1 over 1 squared is the same as 1 over 1, isn't it? Okay, so you guys have seen this stuff before. And look at this. Why is C horizontal?
It's uniform.
Yeah, the electric field doesn't change, so the force is going to be the same. Now you can see that the area under this horizontal line would represent the work that I'm doing if I go this way, right? Let's take a look and look at this. It's going up. Every little rectangle here adds to the previous one to make this line go up. If I started at x equals infinity and said that's where the voltage is 0, forget about it. My line is going to be up here. I'll never have a finite potential energy. And for B, which is 1 over R, you have the same thing. This graph isn't perfect, but 1 over R, the area of that, it should intersect in here somewhere because that's where we're saying the voltage is 0. And this graph here, which is 1 over x squared, it's actually higher up than that, but I've brought it down to make that potential energy 0 there as well. But the idea is that the trends are up and the trend is straight there. I hope you enjoyed that. Okay, I looked at a couple of people's works who sent this in, and yeah, I'm sorry, I was not totally clear. I have something in my head, and then you guys go ahead and just assumed the alpha particle is held fixed. Does it say the alpha particle is held fixed?
No.
No. Oh.
Does it say it's initially at rest?
Mm-hmm.
So what do you think is going to happen?
Gonna move.
Right. It's going to move. So I did it just like we would with the carts colliding and having an elastic collision. And I'm just saying, look, if there was a spring in here, but instead of a spring, we got the potential energy. So I'm sorry, I didn't say that this thing is free to move. I should have said that. So I calculated the center of mass, velocity, and then again, energy initial goes energy final. The kinetic energy initial is the 1/2 mv squared. The potential energy initial, in this case, I'm saying is 0 because it says, assume the proton starts from a great distance. So if it's starting really far away, we'll assume the potential energy is 0. The final kinetic energy is going to be the kinetic energy of the system. When we reach closest approach, they're both moving at the same velocity, same center of mass velocity. And it's both masses. What's my potential energy final? K, Q, Q. Why do I have a 2 there? Oh, I know why. Because this is 2Q. Is an alpha particle, does that have twice the charge of a proton?
Yeah.
Yeah. So I have 2Q times Q over the distance, and that would be the distance of closest approach. So here we go. I just plugged them all my numbers in, and I calculated this. Now, John has almost the exact same answer, but he assumed this thing didn't move, as far as I could tell. I'll have to go back and look. And he got a very close answer here. I kind of have a feeling, for whatever the numbers are, maybe it doesn't matter. I don't know. But I'll play around with that.
Maybe it's just really tiny.
Right. It could be. So what do you think of this problem? We actually did this one before, didn't we? Why do I like the problem? It involves circular motion. It involves energy. It involves electrostatics. It's great. I think most people knew to write FC equals FE.
Mm-hmm.
And there you go. This is the mass of the electron. Then we go to our energy. The initial energy is going to be the kinetic energy and the potential energy. That potential energy is a potential energy due to electrostatics. It will be negative. Can somebody explain to me why this is going to have a negative potential energy?
Because it's a closed system.
I think what you're meaning to say is the total energy is a bound. The total energy is negative when you have a bound system.
Yeah.
But I'm going to say that the potential energy has to be negative because this is a negative charge and that's a positive charge. And for point charges, we say that at infinity, the potential energy is 0. So I would have to add work to bring this out there. I am now going to add the ionization energy to get this thing ejected. And when I do so, the particle will break free and the final energy will be 0. Here we go again. Charge on the electron is also the same as the charge on a proton. That's why I've got Q squared here. This is the distance. You can look it up online. That's the radius. And why don't I have to worry about the mass of the electron? Nobody knows?
Because it's insignificant.
No. Good try though. I like that idea.
Wait, the mass of the electron?
I didn't write the number for the mass of the electron, and in fact, I did not use it in order to calculate this number. There it is. It's in the equation. Why don't I have to use it?
This has something to do with it being a cloud?
Nope. I suggest you look up here. What does this equation tell us?
Mason says it's because the mass of the electron cancels out.
Mason, how do you know Mason said that?
Because he just said in the chat.
See, I just had something flash here, and it doesn't come up on my screen. I have to click on that. And then what do I have to do? Go to chat?
You could have it up side by side, I think.
Okay, I guess I could leave it up there. Holy cow. Okay. Thank you very much. That is correct. So the mass will cancel out. When you put this velocity down here, the electron mass cancels. And look at this. We have an ionization energy of this amount. And what in the world is this? Does anybody know what that is?
Isn't that an electron volt?
It is an electron volt, and I'm going to chat. It's an electron volt. So tell me, what's the value of an electron volt?
Isn't it 2.61 times 10 to the negative 19? No.
Yes, I assume this is Mason still telling me stuff. He says it's a volt, 1 volt, times the charge of an electron. That's an electron volt. So what are we going to do? We're going to come down here. I got to turn this back on. You should know about electron volts, especially if you're going into chemistry. An electron volt will now be 1 eV is equal to 1.6 times 10 to the minus 19th joules. Where in the world did that come from? The charge of an electron times a volt is energy. What is volts? Work per charge. So work is, so this is joules per coulomb.
Oh.
Yeah, so you learned something, didn't you? So if you take this number here and, well, how would I convert now? I got to use this conversion, don't I? I'm going to take this number and I'm going to divide by that number and I get 13.6. If you go look it up on the line,
That's
you'll
it.
find
That's
out
it. Right.
that's
I think it's like 13.8 or something.
No, it's very close to this. You're right. It's very close. My point is that the physics works. It's very good. It doesn't work so nicely with other quantum mechanical states because it gets complicated. And we make some assumptions here. Like, first of all, we're making an assumption that the hydrogen's not going to move, you know? The proton doesn't move. And some of those things don't work very well when you get that more complicated junk. Well, I hope you enjoyed all of that.
It was fun.
Okay. Now, one thing I did not do was I did not pull up a formula sheet for the AP exam.
Here's Google. It's easy to find.
Hey, what's going on here? Dan Mayevsky is zooming me. I'll be on in a minute. Sorry. Oh, boy. I'm waiting. How's that? Okay. Let's see. I'm going to go up here, and what am I going to type in? AP Physics, C, Mechanics.
It's the same review sheet. It's the same formula sheet for both exams. Doesn't matter what you put.
Yeah,
Oh,
it shows,
really?
it shows there's 2 columns. Just go into image. Oh, that works too.
Is this right?
Just go into images.
Just to go to images.
There it is.
Super duper, kids.
They haven't changed it.
Great.
It's 3 pages, I think, not 2.
Well, whatever. Who cares? This is good enough.
This is the B exam. It's not the C exam.
This is not the C exam?
It says B on top.
Oh, the hell with it.
If you look up
find the
physics,
C.
yeah, go back to the other tab.
Hold on. Just you be quiet. You think that's better?
Hooray!
Okay. Here we go. Doesn't this look nice? Everybody understands what this formula is? I'm going to bore the hell out of you, but there might be a couple of things that you want to look at first. I recognize the formula. Somebody's got to say yes.
Yes.
Thank
Yes.
you. And you recognize the format for this one. Who's making all the damn noise?
It stops right away.
Yeah, I don't know what's going on there. What the hell is this formula? I don't recognize this.
I think that might be part of the forgotten formula.
It
Just
is the forgotten
reformatted.
formula. All you gotta do is take the
Yay!
square root of it. That's the forgotten formula. Okay. F equals MA. I hope we know that one. Did you have any idea what this is?
Is that change in momentum over change in time?
Yeah, and what's that equal to?
Impulse.
Yeah, no, it's equal
No,
to
force.
If you brought the dt over, you'd say impulse is equal to the change in momentum. Well, this is how Newton defined a force. We all say force is ma. He actually defined it as the change momentum over the change in time. What is J?
Impulse.
Thank you. It's impulse. So the integral of force times time, that's what we're doing here, is the change in momentum. Finite value of not an infinitesimal. And of course, momentum is mass times velocity. Do you notice they're not using the little arrows over the vectors? They're just saying that it's bolded, okay? The force of friction has to be less than or equal to mu times n. What are we talking about here?
Static friction.
Yeah. I think what they're trying to do is generalize it so it works with kinetic friction as well, because they put the equal sign here, and they're not specifying whether or not we're using static or kinetic coefficient. Capital N represents the normal force. So that's what they're saying, is this force of friction could be either in this case. We all recognize this, right? Work equals the integral of force times.
Mhm.
Okay, great. 1/2 mv squared. So capital K is their kinetic energy. What's capital P?
Power.
And it's the rate at which work is getting done. If we think about honors physics a lot, we just think of work per time. I still think of it that way, but it really is a rate like this. Power is also equal to force times velocity, which we've seen. Now these two things are vector quantities, and this is technically a dot product, isn't it? Same with this. It's got to be parallel. That's what the dot product means.
All right.
Ugh. Ugh. What are they talking about?
That's electrical potential energy, right?
Nice try.
No, well, that's
Gravitational
just
potential.
gravitational.
Yeah.
Gravitational.
They use U
Gravitational
for
potential energy.
the
okay.
subscript G.
What are we assuming about the gravitational constant here? The 9.8. We're assuming it's constant.
You're on Earth.
Yeah. Well, whatever you are on, that's going to be a constant.
Has to be a
Just
constant.
don't use this formula if we start to go far away from a planet, because the gravitation acceleration keeps changing. Centripetal acceleration, right? We're familiar with this.
Mhm.
And do you feel equally comfortable with using omega squared r?
Yeah.
Great. Okay, this is the Greek letter tau. We saw the Greek letter tau in electricity for the time constant, but it's not that. What is it?
Torque.
Torque.
And it's r cross f. Is r cross f the same as f cross r?
No.
No.
No, if you use your right-hand rule, you'll see how that works. Okay, the sum of the torques is equal to I alpha. Does anybody know the name of this law?
Newton's second law for rotation.
Correct. So it's F equals ma for rotation. I equals a little mass times a distance squared, and then you integrate it. So you add up all of your inertias. Same thing with this thing is for finite amounts. This would be, I should say it this way. This is for discrete masses. This is for continuous masses. Oh, my Lord. This is the X. We called it X center of mass. The X center of mass is equal to the sum of all the, what they call moments, mass times a distance, divided by the sum of the masses. It's essentially like getting the torques to cancel. V equals R times omega. What in the world is this? What's this capital L?
Angular momentum.
Very good, angular momentum. This can be thought of as R cross P. What's P?
Just regular momentum.
Yeah, it's linear momentum. I think somebody was chiming in from the bleachers. Thank you, Mason. It is the momentum. And didn't we used to say that it was MVR?
Mm-hmm. Which is
Well,
the same thing as P.
yes, MVR. The reason why we did that was that we just, for the problems we were using, the velocity was perpendicular to the radius. So you have to make sure that you're dealing with a momentum vector that is perpendicular to R. And I omega. Okay, great. We know that kinetic energy is 1/2 I omega squared. And now these are just the kinematic formulas just written for angular terms. Let's wrap this up. A spring, 1/2 kx. Negative kx. Potential energy of what?
Spring.
Yep. The period is equal to 2 pi over omega. Isn't that an interesting way of putting it? Because omega is equal to 2 pi over the period, isn't it?
Yeah.
Okay, so that all works. I told you, you got to be expected to use this or this one. Never know when. Of course, our thread torsional pendulum is better than any of these.
I don't think oscillations is on the exam.
They took that off?
Yeah.
No, wait a second. They gave us a practice problem and it had oscillations on it.
I'm pretty sure I read that it wasn't on it for their unit stuff.
Okay, maybe not, but oh boy, weird. Okay, let's take a look at this one. What is the meaning of the little r hat here? We never use this, do we?
No.
It's a unit vector. All it's saying is that this force is in the opposite direction of the radius from one object to the other. So if your radius is positive, the force is negative. And the reason why they stick that there, even though it's got a unit of, it's got a value of 1, a magnitude of 1, its direction is in the direction. It's a direction vector. So it tells us if you're going this way, the negative says go the other way. So it's technological mumbo jumbo that you probably will not use. And now what about your potential energy from gravitation? That's because we took the integral of this thing and you ended up with R. And now that negative sign is significant in that gravitational potential energy is negative if you assume that potential energy is 0 at R equals infinity. Wow, what a lot of crap.
Yeah, oscillations and gravitation is not on the exam.
This is ridiculous.
It only goes up to rotation.
Okay. Well, you know what? I have a bigger mission in mind. So thank you. How would they put then the question with the thing oscillating on it on a practice problem for us?
I don't get it.
Okay.
They're just throwing things together at this point.
I think so. Let's take a look. Up. We have a chat. Beyond bigger mission in mind. Okay. I'm very happy with that. I'm going to try to have a bigger mission. My mission when this exam is over will be to do something really cool, hopefully. All right. We all familiar with this, right? Okay, now it gets serious. What is this?
Gauss's law.
Yes. I'm going to ask everybody to make sure that you know this. They've cut out so much from this exam. I can't believe this is definitely on there. I can't believe they're not going to ask you a question about this. So what is this? The electric field. This is the area that the electric field penetrates. And we should probably have a separate time where we talk about Gauss's law. We're going to run out of time on this. Okay. So next time we Zoom, we'll talk about Gauss's law. Electric field. Volts per meter is the same thing as newtons per coulomb. Remember that. That's an important thing that kids can screw up on. It also says that if we're moving in the direction of the electric field, my change in voltage is negative. I'm losing voltage when I go in the direction of the field. This is how we add up voltages for all the individual components of a discrete particle system. If you take that voltage and you multiply by Q, you're going to get the potential energy. I think we know, we just talked about that. Here we go for capacitors. Does anybody know what this little K is in this capacitance formula? It's
The dielectric constant.
Yeah, dielectric constant. When you shove a dielectric material in between the parallel plates, you increase your capacitance. So we derived this formula in class. We did that one. Capacitors, that P stands for parallel. If you're in parallel, you add up your capacitors. If you're in series, it's the 1 over capacitance rule. The change in current over the change in charge over the change in time is your current. This is the potential energy of the capacitor. We just did a bunch of those, didn't we? The resistance formula. Now, what in the world is this? Damn it, what is that? That's not. Do they have J here? Current density, holy smokes. You know what? I don't know. I don't remember seeing this one. We'll worry about it another time.
That's
Electric field.
concerning.
I'm not going to worry about it.
I don't think that's
Okay.
going to show up. I haven't
It
seen
comes
a
from
problem.
something
with it.
else. Oh, I know. This is related. This is all related to the drift velocity. Remember we did drift velocities? I said I don't like memorizing formulas for that. I'm going to go down to basics and figure it out. We came up with this formula, but we never really formalized and used it. We said, let's break it all down into parts, and we understood where it all came from. Because that tells you about how fast the electrons are moving in a wire. They move very slow. The impulse, the signal moves at the speed of light, but the electrons themselves, they move very fast. Should we continue on here?
Sure.
Okay, so we were here. Somebody tell me what this formula is for.
Resistors in series.
Great, what's this one for?
Resistors that are parallel.
And you kind of know what's going to be on the test if they cut out half of it, right? I mean, you know they're going to have a circuit on there. So now what about this?
Power.
Yep,
Power in a circuit.
yep.
That is your magnetic force.
Are you
That's
telling me there's no magnetism at all?
They
On this?
cut off both units that include magnetism. That's the funny part.
Gee whiz. Well, you know what this is, QVB, and it's a cross product. I'm still going to talk to you about this. Does anybody know what this is?
That's
Gauss's law.
Gauss's law for magnetism.
Lenz's law?
Isn't it? Wait, no. That's the
Yeah, it's not Gauss's law.
Bio something law?
Lorentz or whatever.
Start with an A.
Ampere's law?
AM.
Ampere's?
Amperes. It's Ampere's law.
Oh.
All this is telling you is that if you take the integral of the magnetic field as you make a loop over that length, it's proportional to the current passing through that loop that would create that magnetic field. And this is the Biot-Savart law.
Biot-Savart, that's the one I was thinking. Alphonse Laurent.
Only one problem here. Do you remember it having an R cubed on the bottom? I mean, I remember R squared was on the bottom. And then you see what they've got up here? They've got a cross product.
Yeah.
But I thought that was an R hat. Well, we won't have to worry about it for the exam, but I'm definitely going to come back and look at this.
Oh, I have it printed and it's R squared on the bottom. And it has
Yeah, no, it is on this the random website too.
Here,
R
if you
squared,
look at
right?
if you look at my screen,
Oh, let me look at your screen.
can you see it?
Can I get your screen to be big? No, wait. I have to stop sharing to make your screen big. Hold it. I'm going to stop sharing. Go up another inch. Oh, they express it a different way, don't they? All right, cool. All right, I'm going to go back to sharing my screen. Okay. Well, in any case, that's interesting. Boy, that, I don't know. I got to think about what they're trying to do here. ILB, that's what this is, isn't it?
Mm-hmm.
Yeah. And they're doing it in case, you know, the L is, it's for a curve, I guess is what they're talking about here. Do you remember this one?
No.
This is the
Not,
magnetic field inside a solenoid. That's
solenoid.
why they got the S there.
Oh.
Yeah, we derived that using Ampere's law. And now, what is this?
Is that Gauss's law?
Yeah.
Gauss's law. Okay.
Yeah. If you put the little closed symbol here, that means you've integrated over a complete closed area, a volume, I should say, the area surrounding a volume. What does this tell you about the magnetic flux? You remember, it's zero. Do you remember that?
Yeah. If you do it over the entire area, right?
Yeah, it's got to be closed around the whole thing. It's like, if you can see my hands here, it's around the whole.
Mm-hmm.
It means that there's no magnetic
Flux.
monopoles.
Mono.
Yeah. The magnetic flux is zero. Here, I'll show you what I mean. Here's a magnet. Let's say this side's the North Pole and that side's the South Pole. Here we go. North Pole, South Pole. If I surround this thing with an area like this, the magnetic flux that comes out of the North Pole and goes into the South Pole, there's going to be flux coming out of this area and flux going into the area. Net flux is zero. You can't have a magnetic monopole. So how does that work? If I break the magnet up into two parts, I automatically get a South Pole here. I automatically get a North Pole here. So you can't separate these poles. That's what that means. You do remember we had a conversation about that, right?
Not even protons are monopoles.
Whoa. Who said protons aren't monopoles?
You said it, remember? You just said that the it's just parts of positives and negatives spinning.
Are you thinking about the neutron?
Am I?
I think you are, Adriel. Yeah.
Oh crap!
If
I don't
you
remember
take
him
a
talking.
neutron and that's neutral, it has a proton and an electron in there, and part of the neutron is positive, part of the neutron is negative. And I don't know much about this, believe me, but they say that when these neutrons spin, that you can get some kind of a magnetic effects or something out of this. I don't know. I don't know much about it. I should shut up now. But the proton, oh damn it. If you have a proton and it's rotating, you need to know the direction of that magnetic field. So the proton itself will have, it's a monopole electrostatically, but it won't be a monopole magnetically. You're going to have a North Pole and a South Pole that you can't separate. Okay. All right. EMF, this is magnetic induction. Change in flux and change in time. This is the inductance, right? Change in current over change in time. I can't believe it. We spent all this time trying to finish this up and do it, and you're not going to do any of it. Oh, well, that's the magnetic potential energy of an inductor. Now, don't you feel better?
Mm-hmm.
Not really, huh?
Did you know you get a copy of our answers?
Yeah, that's part of their plan to prevent cheating.
Oh shit.
Isn't that ridiculous?
Yeah.
Like
There we go. Now
teachers
I
are
get
gonna
to
care,
see
sure.
Huh?
I think they will.
Teachers
what are
aren't
you-
gonna care if their kids cheated.
Oh,
on the
I can't imagine under these circumstances.
I don't like it doesn't make sense.
Right.
Like if a kid cheats on the AP exam, why does that matter to a teacher? Like, yeah, if it was on a test in school, sure, but
Well, the message that they sent out was that by sending this work to the teachers, they're hoping to make the kids think twice before they do something stupid, because it's possible that a teacher is going to look at this and say, no, that's definitely not that kid's work. Well, what are we going to do about that as teachers? Am I going to contact the college board and say, hey, this isn't the kid's work? I guess I could do that,
are you
Who
a
knows?
snitch though?
Look, there's not that many of you, but there are AP teachers like Cockrell. Holy cow, she's got so many kids. I can't imagine she's going to scrutinize this work and try to figure out if you were on the up and up,
Mm-hmm.
Well, okay. Well, it's been a wonderful evening. I wouldn't mind talking more if you've got things that you want to talk about.
Do you want to talk about?
What do I want to talk about?
Period is one of the frequency.
Oh, I don't know.
Can we talk about like PE and how like it's if you're not all the way out, then it's a negative number? Like I can't wrap my head around that for some reason.
Yeah, I always have trouble with that stuff too. Let me stop sharing and I'll go to a whiteboard. Okay. Are you talking about like charged particles or something, or give me a context to do this with?
Particles.
Charged particles.
Yes.
Okay.
Coulomb's law.
Okay. What do I have going on here? Let's keep this fixed so it can't go anywhere, okay?
Mm-hmm.
Positive charge going out this way. Now, there's going to be an arrow force vector acting on this thing, and that force vector is this way, right?
Mm-hmm.
This is the force electrostatic. And I sometimes like to ask myself, what would I have to do if I wanted to bring this charge over this way? Now, I like to think of sometimes that I'm pulling it. Now, if I pull it in this direction and the distance that I move is also in the same direction, I'm going to say that I did work.
Mm-hmm.
If I do this work, I'm setting up my problem. I'm only going to do the minimum work needed to get it over here. If I did extra work, then by the time I get here, the thing's got a velocity, and I don't want that. So that means this pulling force will be equal to the electrostatic force the whole way in. What do you think of that?
Okay.
So what is going to happen when the particle gets to here? Can I now say that my work has been stored as potential energy?
Yes.
So I don't know. I'm just talking, kind of expressing a little bit about how I see this. So the electrostatic force is the way the book would usually describe this. And they would say the electrostatic force is looking like this. What did I just do? And the change in potential energy would be that area.
Okay.
If I use my force times that distance, then my force is actually a negative force times a negative distance, and I'm going to have positive work being done. But what about if I use this force? I've got a positive force and a negative distance. So the force is positive and the distance is negative. So how much work is being done by the field? It's negative work. This is how come we have to say that the delta potential energy has to be equal to negative the work done by the conservative force. My hand is not a conservative force, but the conservative force is conserving energy because it's doing negative work. It's doing that negative work and then it stores it. When I let go from here, it's now going to do positive work. When I go this way, the field does negative work. When I go this way, the field does positive work. And that positive work would result in a drop in my potential energy. Now, I don't know how much more you want me to talk about, but that's kind of like the basics of where that negative sign is coming from. I like to go back to stuff that I'm familiar with, namely gravity.
That one's also kind of tricky.
Yeah. When I lift something off the ground, and I like to use numbers to prove my point, you know? And I can't tell you how many times I've done this myself. Let's say this thing weighs, I'll put the arrow in here. Let's say it weighs 5 newtons. And now I'm going to lift it a distance. But I'm not going to lift it with any extra force. I'm only going to lift it with just enough force to move it. If I use 5 newtons times, let's say, 10 meters, then I'm doing positive work.
Mm-hmm.
Gravity is doing negative work. But you know that when the particle gets up here, it's got positive potential energy. How do I know? Because if I let it go, it's coming back down. The potential energy drops. So again, it's the same idea. The change in potential energy is equal to negative the work done by the conservative force, that being the conservative force.
Mm-hmm.
They define it this way because, look, I could put in any force I want to. I could put in more force. I could put in 20 newtons. And the work that I do will not be equal to the change in PE.
Mm-hmm.
So I guess that's it. Is there anybody still on with us?
Hi.
Yeah.
Look at all those people.
You have
Well,
friends.
Honestly, well, I think all of our lives, you don't realize how much social interaction there is until it's gone. This is like living in a vacuum. I mean, you guys are pretty used to texting everybody all the time. I guess that's normal. But I'm used to going in there and actually having a brar give me a bear hug and pick me up off the floor. Well, okay. Anybody else have anything that they wanted to discuss? Tomorrow we don't have class, but what else am I doing? I'll be happy to talk to anybody if you had questions or you came up with some other example problems you wanted to talk about. I think the most important thing, if you're going to take the AP exam seriously, is obviously they want you to understand that physics is about supporting observations that you make in a laboratory experience. I'm sure there are certain theoretical physicists who would be offended by that, but they really want you to concentrate on thinking about how would you set something up for a lab. And that's why I put that question in there not too long ago about where would you put the photo detectors in order to measure the velocity or time the period or something like that. I'm sure there's going to be stuff like that. That's what they want you to do. Okay, well, if you've got nothing else to do, I'm going to give you a problem then. You want to try something interesting?
Sure.
Something fun.
It's fun. Now, don't call it out. Okay? I don't want anybody to give this thing away. I happen to have a dog. Look at this. Does it look like a dog yet? Whoops.
It's already dead.
Here we go. I got a dog. And the dog's got a nice tail. I should have just drawn it with this thing. Whoops. Hey. Okay, and so now this dog is going, now it's a cat. The dog is going to have a can tied to its tail. And the dog is going to be moving forward at 1 meter per second. Every time the can hits the floor, the dog gets startled and doubles its speed.
Oh shit.
And this is a predictable bounce, or
It doesn't
Exponential
matter.
dog.
It could happen at random. It doesn't matter. Every time the can hits, the dog gets startled and doubles its speed. What is the maximum velocity? Do not call it out. Get everybody a chance to think about this.
I feel like I've seen this problem before.
Yeah,
Did I do it
we've
last
done
year?
this before.
I don't know, but
I remember you drawing a dog on the board.
I remember that too.
Shoot. I thought that we didn't do it last year.
I don't remember it.
Well, if Dan,
I don't remember how to answer it, but I remember
Alright.
seeing something like this.
I know where to
so
start, I
it
think.
doubles its speed every.
Every time it hits the floor.
Yeah. Do you know that I gave this to the honors physics kids on their last multiple choice test?
Hmm.
And I'm still alive. They didn't find me and kill me. I think they hated me.
Can I offer an idea?
Who's ready to talk about it? Everybody's had a chance now to think about this.
Dan has an idea.
I
Go
have
ahead,
an idea.
Dan. What's your idea?
So that can, every time it hits the floor, it comes up again, but not as high. So is this a momentum problem?
Nope. It's not a
Okay.
momentum problem.
Okay.
Because as long as the dog keeps running, it'll keep putting energy.
Right, exactly. The dog is going to keep running, and I have no idea how often the can hits the ground.
Okay.
But eventually, it's going to hit the ground. You can just picture that, right?
But eventually, it's gonna get to a speed where it's just flying
of
off,
light?
right? And
It's
it's
gonna-
not hitting. It's not hitting
Okay.
the ground anymore.
There
right?
are people who say it'll be infinity because you can always keep doubling your speed. And then there are
Mhm.
people who say, no, you can't go faster than the speed of light. So wouldn't it be natural if most people would say it's the speed of light then?
Yeah.
Okay.
Isn't there a point where you're just dragging the can along and it's not hitting the ground anymore?
Well, that I suppose that's possible. I mean, if you were going to travel that fast, the cat will burn up in the atmosphere too. So, I mean, we have to be reasonable here. What kind of reasonable assumptions can you make? The problem is absurd. Okay, you really want to know the answer?
Yeah.
I'm scared.
Some people say it's the speed of sound.
Oh,
Oh, that's where we did it last year.
Because
Why is it the
it,
speed of sound?
it can't hear when the can hits
Right.
the floor.
Exactly.
because
So
then the sound
if
will just
you're
be behind it. Oh wow.
What if the thing was traveling at 341 meters per second? Any ringing won't get to him because the sound is only going 340. Now tell me that's not a good problem.
That's a great problem.
Okay. One, Dr. Puga made this problem up. He's the guy with the PhD in physics who retired. Okay. He was from Bell Labs. I love this thing. He made this up. He used to give this thing to other people at Bell Labs and they couldn't figure it out. They would all say it's the speed of light. But no, it helps to know that this is made up for our chapter on sound. No question about that. But you know what? Some kid in honors physics answered it with a different number. And I think they might be right.
What did he say?
512 meters a second.
Why?
Because the last one is going to be underneath this.
Because why? What?
And then you double it after that. Okay.
Go ahead, double it. What do you get?
2, 4, 6.
Close. Close.
2, 4,
Sick.
8, 16, 19.
What comes after 128?
130.
Oh, come on, come on, come on.
256.
256.
Well, now wait a
512.
minute.
Then
wait a minute.
512.
If the can hits at 256, the dog will still hear it.
Oh.
And it will double.
And so the dog will go,
512.
But that's it. That's the last time we'll hear it again.
yeah, right. Now tell me that's not cool.
Who was this kid?
Where's his PhD?
I would have to go back to the test and look. I forgot who did it. But there was one kid definitely had that 512, and I thought, oh my gosh. And I don't even know if Dr. Puga ever thought about that. But now here's another question for you. Could the dog still hear the can, even if you're traveling faster than the speed of sound?
Is it in front or behind of him? If he starts running towards the can.
Oh, good point. What if the cat was turning around? Okay, no,
Yeah,
my
if he starts
point
running,
is,
if he starts chasing his tail.
if you put your fingers in your ears, can you hear yourself talk?
Yeah.
Yeah.
Because
Wait,
the
why?
vibrations go right through your body.
Uh-huh.
You can put your fingers right on your throat and you can feel the vibrations.
Yeah.
Mhm.
So remember last year I took a tuning fork and I put it on a kid's elbow even with their finger in their ear and they could still hear it.
Mhm.
You can
It's-
hear if this thing is tied to the tail and it's
Oh.
actually touching the tail, that dog is going to hear it through the vibrations of the body. And that's something else that we talked about in this chapter on sound. So Dr. Puga didn't think about that one. So I had him.
Will he hear it or just perceive it?
Well, the vibrations are only vibrations until we say that we perceive it as sound. So the old saying that if a tree falls in the woods and no one is there to hear it, did it still make a noise?
No, it made
Or
a
did it still make
vibration.
sound? Well, technically it made a vibration, but if nobody was there to hear it, it wasn't a sound. Now that is, some people might disagree with it, but it's kind of like a technicality. Some people say that these are vibrations until we perceive them as sound. Pretty cool?
Well, science comes from philosophy.
Oh, yeah. Well, there is a hierarchy. You've heard of the hierarchy of the sciences?
Mhm.
Yeah, and I hate it.
Well, I don't know. I mean, somebody structured it. I think it's kind of cool. Physics is so fundamental, but what is more fundamental than physics?
Mathematics,
Math. And what's beyond more fundamental than the math?
philosophy.
Philosophy. I once had a student who went on to become a math major at college, and he told me that biologists wish they were chemists. Chemists wish they were physicists. Hold on, I'm going to blow the punchline.
Physicists wish they were mathematicians.
Yeah, but I think you skip that one and you say, and God wishes he was a mathematician.
I don't get it.
That mathematicians are above everybody, and even God would want to be a mathematician.
Oh.
But
No, they say that they're above everyone.
yeah, but how do we know that God's not female? So I don't know. Okay.
Hmm.
All righty. Well,
You have any more questions like that?
I don't know. I'm just trying to see who else is still here. We have, is that Jordan Totten?
Yeah.
Oh, both
And
Jordans are
Tetzel.
here. So Jordan, holy smokes, if you turn on your faces, we could do the Brady Bunch. I can see you. Well, Akil is still, Akil, are you really still there? Oh my gosh. What have you been up to, man?
No, bro's next video is everybody going to be doing a lip sync in AP Physics.
I don't, Abrar threatened that he was going to do a video. I haven't heard anything.
What do you mean threatened?
Well, I mean, come on. Man. Every time Abrar does a video, I got to worry about my job.
Are you gonna voice act in his next video?
Am I going to what?
Voice act in his next video.
Voice act. I guess he could use my voice, I suppose. But I got to be careful. I'm telling you, even under these conditions, I want to teach next year. Man. And Morgan, how are you tonight? Morgan, are you there?
Yeah, I'm here.
How are things?
Good.
You're lying, aren't you? I'll tell you a little about, you can see my face, right? Have you noticed it's getting worse and worse every time we get on? By the end of this whole thing, I want to look like the coronavirus. I want to have all this point sticking out all over the place. That's my goal. Oh my goodness. Don't you miss screwing around in class, huh?
Yeah.
Yeah.
Mm.
What do you mean
Well-
you could do even worse stuff here?
I suppose what we could do is get a video game. Maybe we should play ping pong on Zoom or something. Alice would definitely join.
Oh yeah.
Man. Oh goodness. Well, you know what I'm going to do? I still have a couple of minutes left. Do you mind if I talk to you about another problem?
All right, go ahead.
Okay. Oh, look at who I see. I couldn't see all that drawing before. This is what I asked. I think I talked to you guys about this problem last year, but right now I've got kids in honors physics that are working on this thing, and I think they've got it figured out. But I'm going to get on the computer with Rumesa because she's learning how to program, and we're going to just do a quick little problem. The ball falls to the floor, but it bounces up to 9/10 its original height. Do you remember this problem?
Mm-hmm.
And then the next time it bounces, it's going to bounce to 9/10 of that height. And then it's going to bounce. Why do I keep doing this? I don't have to. It's going to bounce to 9/10 of that height. So I'm moving the ball over to show you that it's just not, bouncing. It'd be hard to show this like vertically. I'm going to show it as it's going this way. So how long do you think it'll bounce for?
Infinity.
Now, don't you
Just
think
keep
that there
going.
would have to be an infinite number of bounces?
Yeah.
Got to be an infinite number of bounces because 90% of anything is still going to be something, and it's just going to be going. But will it bounce forever in time?
I mean, eventually they're going to be so small that its base is going to look like it's not bouncing.
I have I don't know where my ball went. Okay, anyway.
Isn't it kind of like the question like if you and then I have to think about this.
I know what you're thinking of. Zeno's paradox.
Yeah, it's where you take it's like you want to finish like a race.
Yep. And you're
yeah.
never going to get there.
But you just if you keep because you could keep cutting the time like you want to travel
Halfway.
a certain and then you keep cutting it in half.
So he said that you could shoot an arrow at him and you will never hit him because the arrow has to travel past the halfway point. And then it'll have to travel past the next halfway point. It'll keep having to travel past an infinite number of halfway points. And you could never have an infinite number of anything. But there's definitely an infinite number of halfway points. You couldn't cross them though, could you? What is the resolution to Zeno's paradox?
Isn't it with something with time?
You start to cross the halfway points at an infinite rate.
Huh?
Well, if the distance to the halfway point goes to 0, you will be crossing an infinite number of halfway points in a given amount of time. The rate
Okay.
at which you cross the halfway points increases.
Yeah.
So let's look at this problem here before we run out of time. There will be an infinite number of bounces, but will the total time be infinite, or will the total time be a finite value? Because each time becomes less and less and less and less. You get it?
Mm-hmm.
So I'll leave that for you guys to think about. You thought I was going to give you the answer, didn't you?
Yeah.
Well,
I gotta go watch a video real quick. I'll be back with an answer.
did you ever do a geometric series in math class?
Yeah.
Yeah.
Yeah, that's what this comes down.
They told us it was scary and they didn't want to talk about it.
What, the geometric series?
Yeah. Too bad I was like, screw you. You're learning it anyway.
Okay. Well, you know, I can't keep track of all the mathematical techniques. There's so many things. But you could write a computer program in about 4 lines that would take care of this problem.
Oh, these problems are called super tasks. I just clicked in my head.
What? Super tasks.
You just it's like doing a task to infinity, but it's doable.
Oh, okay. I get